Hello students, in this experiment you will verify the Faraday's law of induction. So the objective of this experiment is the verification of Faraday's law. I am Dr. Praval Pratap Singh Bhadoria and this video lab has been produced with the help of Mr. Manjit Singh. This will go in this running sequence. In the introduction, we will discuss what is the meaning of electromagnetic induction and how it is related with the magnetic flux when a coil is put in a varying magnetic field, which is the Faraday's law. Then the methodology for the verification of Faraday's law will be explained, the principle will be discussed, which will be followed by experimental setup and the procedure, and of course the precautions. As a part of the apparatus, a strong permanent magnet, a coil with multiple turns of copper wire will be used. For the measurement of EMF and time period of oscillations, a set of voltmeter and ammeter and a stopwatch will be used. In the circuit, we will use a diode, capacitor, high resistance and connecting wires. So let us start with the electromagnetic induction. So what is it? When the magnetic flux attached to a coil varies in time, an EMF is induced in the coil. If the circuit is closed, then a current flows in the wire. This phenomena is known as electromagnetic induction. The induced EMF is directly proportional to the rate of change of magnetic flux. This law is known as Faraday's law. Further, the induced EMF opposes this change. This is the Lenz's law. If you express the EMF by E, then Faraday's law reads E equal to minus d phi over dt. Since magnetic flux can be written as magnetic field induction multiplied by the area, so phi is equal to B into A, so it can be written as E equal to A dB over dt, or it can further be written as minus A dB over dr multiplied by dr over dt. Here dr over dt is the velocity of the magnet and dB over dr is the space derivative of the field. So one can say that the EMF is directly proportional to the velocity of the magnet. It is what to be verified in this experiment. To verify this, we have a setup in which there is a coil of copper wire through which a magnet attached with a semicircular bow-shaped stand can move with different speeds. Whenever you need to move the magnet through the coil, you displace the stand by any angle and leave it to gain some speed. When this magnet passes through the coil, an EMF is generated in the coil. We shall note down this EMF for different speeds of the magnet. Let us talk how we do it. Firstly, we discuss how to deal with the velocity of the magnet. The linear velocity is given by V equal to R omega. Here R is the radius of semicircular path of the magnet and omega is angular velocity, and it is given by omega equal to 2 pi into frequency or 2 pi divided by the time period t. So the velocity of magnet is calculated by V equal to 2 pi r divided by t, or the velocity is inversely proportional to the time period of the oscillation. So we have the formula now for the velocity of the magnet in terms of the time period of the oscillation. Next, to measure the EMF generated in the coil, one can directly connect the voltmeter to the terminals of the coil. But you face a problem this way, as the EMF in the coil may be the small enough to be measured accurately by the voltmeter of finite threshold. So if this EMF is less than the threshold of the voltmeter, then you cannot measure the EMF of the coil. So we may connect a capacitor to the coil and oscillate the magnet multiple times, say n times. By doing this, the capacitor may get charged to the voltage n times E, where E is the EMF of the coil and n is the number of oscillations of the magnet. And then the value of Ne will be measured by the voltmeter, which when divided by n will give you the EMF. Yet there is another issue. While oscillating the magnet, the EMF of both signs, positive and negative, will be generated in the coil that will reach to the capacitor and will cancel each other during the charging the capacitor. So ultimately, the capacitor will not get charged. To overcome this difficulty, let us connect a diode with any terminal of the coil. This diode blocks one direction of the current and the capacitor gets charged to Ne voltage by an oscillations of magnet through the coil. So we have all the components with us to measure the EMF of the coil. So this is our circuit. The coil is connected here and with a high resistance and diode. One of its terminal is connected to one plate of the capacitor. Another terminal of the coil via a galvanometer is connected with another plate of the parallel plate capacitor. To measure the voltage stored in the capacitor, this voltmeter can be connected with the two plates of the capacitor whenever required. Let us talk about the procedure to be followed in order to verify the Faraday's law. For this, we need to vary the velocity of the magnet passing through the coil. We can do this in two ways. One, we can start oscillations of magnet by displacing it to different initial angular amplitudes. The initial angular amplitudes of the oscillating magnet can be seen in D-shaped scale in the setup. You can start oscillating the magnet with say 75 degree, 70 degree, 65 degree and so on and measure the time for a complete oscillation. Then the velocity of the magnet while passing through the coil can be calculated as explained in the previous slides. The velocity of magnet can also be changed by changing the moment of inertia of the system with the magnet. For different moment of inertia, the system will give different velocities of the magnet even if it has the same initial angular amplitude. To change the moment of inertia, two equal masses are connected with a diameter rod of the semicircular bow-shaped stand. You can change the position of masses to change the moment of inertia and thereby change the velocity of the magnet. Again, by measuring the time period of the oscillation, the velocity of the magnet can be calculated. Now, let me show you the demo of how you will measure the time period and the EMF of the coil. First, let us perform the experiment by varying the velocity of the magnet by varying initial angular amplitude. You start oscillating the magnet say from 65 degree and wait until 10 oscillations are completed like this. So, 1 oscillation, 2, 3, 4, 5 oscillations, 6, 7, 8, 9 and 10 oscillations. Note the time taken by the system to complete 10 oscillations using stopwatch. Also, note the voltage up to which the capacitor is charged using the voltmeter. This is your first observation. Now, after discharging the capacitor by connecting both the terminals of the capacitor, start another observation. This time, let us start oscillating the magnet say from 60 degree. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. You need to take note of such many observations for many initial angular amplitudes. Note down all the observations in this table. You need to note the time periods for 10 oscillations. So these values divided by 10 will give you the time period for each initial angular amplitude. This will give you the velocity by 2 pi r divided by capital T. The voltage for each angle theta must be written here, and these values divided by 10 will give you the EMF. These observations with varying velocity can be done by changing moment of inertia of the system by changing the position of masses attached with the setup. Let the position of masses is 25 centimeter from the axis of oscillation. Now for defined initial angular amplitude say 65 degree, note the observations for time and voltage for 10 oscillations. So this is 1, 2, 3, 4, 5, 6th, 7th, 8th, 9th and 10th. So time in stopwatch and the voltage in voltmeter must be noted. Now repeat the observations for different positions of masses but same initial angular amplitude 65 degree. Let the position of mass is now 23 centimeter from axis of oscillations this time. This time also you need to take note of such many observations for different position of masses but same initial angular amplitude. Note these observations in this table. Here the position of masses x must be written in this column, and as a function of x you need to take note of small t, capital T, velocity and the total voltage up to which the capacitor has been charged and the EMF. Let us once review the table of observations. In this column you need to take note of theta or x, then time for 10 oscillations and the voltage for 10 oscillations. This time divided by 10 will give you the time period and then it will give you the velocity. The voltage divided by 10 will give you the EMF. Now to verify the Faraday's law you need to draw a graph between the velocity of the magnet at x-axis and the EMF for each velocity of the magnet at y-axis. This graph must be a straight line. At last, let us talk about the precautions and sources of error in the experiment. So in the measurement, note the readings carefully. The capacitor must be discharged before oscillating the magnet. Otherwise, the EMF by next oscillations will become erroneous. And the special care must be ensured in measuring the time using stopwatch. The magnet must be hold stationary when the magnet completes 10 oscillations. There may be a friction in axis of oscillating magnet frame. This may make a difference between angular amplitudes of the first and 10th oscillation. At last, increasing the number of oscillations may bring the difference in angular amplitudes, but it may increase the voltage efficiency also. So 10 is a good enough number. I hope the experiment is clear to you, and all the best for your lab.